Circular motion is such a common phenomenon that it's nice to have some tricks for describing how objects can move around circles. So for all of these examples, we're going to start with the basic idea that to parameterize a circle, you should use sine and cosine together with the radius of the circle. So x is going to be r cosine of your parameter, and I'd like to use t for the parameter instead of theta for reasons. And y is r sine of the parameter, which again I'm going to use t. So these parametric equations do trace out a circle of radius r, but they trace out the circle of radius r in a particular way. So here's a circle of radius r. These parametric equations start at the right-hand point on the circle, and it moves counterclockwise at a particular speed. So it turns out that it moves at a speed so that the period of this motion around the circle is 2 pi. So it takes 2 pi time units to travel around the circle once. If you want to start at different points along the circle or go in a different direction or at a different speed, you have to modify this sort of general idea for parametrizing a circle just by changing some things up. We'll see you can change a phase, you can swap sine and cosine. There are different things you can do depending on what you want to accomplish. So let's look at some examples. First, let's parameterize a circle with radius 3. That should be no problem. Centered at the origin, that's no problem because our general idea for parametrizing a circle is centered at the origin. Going counterclockwise, fine. Starting at the top. So it's this starting at the top that's going to be a little bit different. And there are 2 ways to do this. So one way is, so we can use our general template for parameterizing a circle. So x is r, which is 3, times cosine of t, but I'm going to leave this angle blank for a minute. And y can be 3 sine something. But since we want to start at the top, right, we don't want our initial angle to be 0. So if we just put a t in here, when t is 0, the initial angle would be 0. But that's not what we want. When t is 0, we want the initial angle to put us at the top. So we need to add whatever our initial angle is. And to be at the top, that initial angle would be pi over 2. Okay, so that's one way to get a parametric equations for this situation. Another way to get parametric equations for this situation is like this. So we know the radius is still 3, but one thing you can do is, if we want to start at the top, that means x should start at 0 and y should start at 1. Well, the usual way of parametrizing the circle, x starts at 1, or whatever the radius is, and y starts at 0. So we just sort of want to interchange which one is starting big and which one is starting at 0. So I guess that means we could just interchange sine and cosine. So we could use sine t for x and cosine t for y. Right now, when t is 0, we're going to get, right, sine of 0 is 0, so we get 0, and cosine of 0 is 1, so we get 3. So this almost works. It starts in the right place. It starts at 0, 3, the top of the circle. But as t increases, cosine, so let me draw the circle, so like this. So we're starting at the top like we wanted. But as t increases, cosine gets smaller and sine gets bigger. So our x-coordinate gets bigger and our y-coordinate gets smaller. That's going to send us this way around the circle. But that's the wrong way around the circle. We wanted to go counterclockwise. Well, to go counterclockwise, we just need to make our x-coordinate go negative instead of positive. So we could just put a minus sign in front here. All right, and that would do it. Let's look at another example. So let's parameterize a circle with radius 5. That should be no problem. Centered at the origin, no problem. Going clockwise, so we're going to have to be careful about that. and starting at the right-hand side, so that's also no problem. Okay, so radius is 5. Since we're starting at the right-hand side, it seems like we should start with cosine t and sine t. So this will, right now when t is 0, cosine is going to be big, sine is going to be small, and so we're going to start at the right-hand side. But as t increases, y gets big, and y gets bigger because sine grows, and cosine gets smaller because cosine starts big and gets smaller. And so that's going to send us this way around the circle. But that's the wrong way around the circle. We do want our cosine value, our x-coordinate value, to start big and get smaller, but we want our y-coordinate to start at 0 and go negative. So rather than having a positive sign here, we should have a negative sign like that. There is another way to do this, which is, let's start with the same idea of using cosine and sine. Okay, so this, as I currently have this right-hand column written, it is going the wrong way around the circle, but to reverse the direction, well, that's just like reversing time, so we could just throw minus signs on our t in here. Now when time increases, the angle inside the trig function decreases, and when you start at 0 and the angle decreases, cosine gets smaller and sine goes negative. And so that also accomplishes what we wanted. So either of these would be fine. Notice that these actually are exactly the same. It's just the symmetry properties of sine and cosine mean that the minus sign inside of cosine doesn't matter, and the minus sign that's inside of the sine function, you could actually move out in front. Okay. Final example here. Let's just, this is sort of going the other way. Rather than having a description of some circular motion and coming up with parametric equations, here we have parametric equations for some circular motion, and we want to describe what sort of circular motion this is talking about. So one thing we should definitely describe is the radius of the circular motion, also maybe where it starts, and which direction it's going. And also we might want to figure out how long it takes to make one trip around the circle. So that, I guess we could call that the period of this circular motion. Okay, well, the radius, right? The radius is always just sitting in front of your sine and cosine. So the radius here is 7. To figure out where this starts, maybe we should just plug in t equals 0 and see what happens. So we have a circle with radius 7 here. Let's plug in t equals 0. For x, we get 7 times sine of 0, and that's 0. So x starts out at 0. And when t is 0, for the y-coordinate, we get 7 times cosine of 0, that's 1. So 7. So when t is 0, these parametric equations start at 0, 7. So that's at the top of the circle. So we're starting at 0, 7. That's the top of the circle. Okay, now let's see which direction we're going. Oh, I see I've been using t instead of theta here. I use theta right there. Okay, so now let's figure out which direction we're going around the circle. So just imagine that theta starts at 0 and then increases a little bit. So when theta increases, 2 theta also increases in the positive direction. And when the angle increases, sine gets bigger. So as theta grows, x also grows. It starts out at 0, but then it goes positive. Okay, now let's think about the y value. So when theta is increasing, 2 theta also goes positive. And cosine, as the angle inside of cosine starts at 0 and increases, cosine itself decreases. So as theta increases from 0, our y-coordinate decreases. So we're starting at 0, 7, but then x gets bigger and y gets smaller, and that means we're going this way around the circle. So it looks like the direction that we're going around the circle is clockwise. Okay, for the period of this motion around the circle, well, we have a 2 for our coefficient inside of our trig function here, inside of cosine and sine. And one thing we've seen is, so earlier we called that value omega, and it's 2. It's an angular speed. And we've seen that omega is 2 pi divided by the period of our motion. So we have 2 equals 2 pi. Now we can just rearrange this to solve for the period. The period is 2 pi over 2, and that's pi. So the period of this motion is pi. It takes pi time units for this point to travel around the circle once.